morning, good afternoon, or good evening, whenever you watch this video. Today I'm sitting here with Leo Veldhuis. Leo is a full professor in the chair on flight performance and propulsion, and he is an aerodynamics expert. So the topic of today is aerodynamics. We've prepared a couple of questions for him. So the first question is if you're designing an aircraft or more general an air vehicle, drone, whatever, there will be aerodynamics experts in the teams. What's the first thing they need to do? Do they start looking for airfoils or these kind of things, or do they need to do completely different things in the beginning?
Well, obviously, first of all, you would look at what is actually the mission of the vehicle. Can be an aircraft, can be a small UAV type of vehicle, whatever. So you would like to talk about the top level requirements. What is the typical mission? What does it have to achieve? And then based on that, you can determine the flight speed, for example.
Mm-hmm.
And that is a key parameter that determines the subsequent aerodynamic analyses.
So okay, so not immediately looking into airfoils, but just mission requirements, and then
and obviously nowadays also it's important to look at what do we face the design of a sustainable aircraft. So also the energy source is an important parameter now. Is it an electrical vehicle or not? These things will influence the external shape, and that shape needs to be accommodated by the aerodynamic designer.
Okay, what would make a good aerodynamic design? Are there key things you need to check?
Obviously, an important thing is that the so-called lift-over drag ratio needs to be high, especially if you talk about cruise conditions. And so, if the major part of the mission is for example the cruise, you'd like to have a good L/D ratio. Well, that's certainly not the only thing that you would look at. Another thing that is important, for example, for low-speed application, for ground handling, for short takeoff and landing, is the high lift capability. As for some vehicles, you'd like to have it to operate on short runways. Then suddenly the high lift system and the design thereof needs to be also looked into. And last but not least, also important, how is the propulsion system integrated? If it's a vehicle with a propulsion system, it doesn't have to be, can be a sailplane, but if it has a propulsion system, then what type of propulsion system fits the speed? And once you selected that, how is it integrated? And nowadays you can, and people are doing so in also international projects, is look at the best integration of the propulsion system. Because of this integration, you can even improve the performance of the particular vehicle.
Okay, so there's many aspects you need to take into account.
And then what maybe some people forget is that, especially those who go to look at, for example, good airfoil shapes, that you operate the aircraft in a certain environment. So say that you operate it at low speed in a lower atmosphere, then also the sensitivity to the environment becomes important. There's airfoil shapes that are sensitive, for example, for dirt or for turbulence or for rain, and this may degrade the performance of the airfoil.
Okay, I saw that you brought some books. Where should students start looking for these kind of parameters?
Yeah, well, here is an interesting, somewhat older book. It's called Theory of Wing Sections. Some people regard it as the Bible on airfoil shapes. It's from NACA, so the predecessor of NASA. It contains a lot of information on airfoil shapes, but it must be said that this is sort of somewhat older airfoil shapes, not always good enough for your design. It's a good starting point, but some people would like to improve their airfoil shape and to, for example, to allow for more laminar flow, a lower drag, and then you would, change maybe an existing airfoil to have a better low drag performance. Well, this is certainly a good starting point.
Are there online tools in which this kind of things are available nowadays, where students can make a quick estimate on the performance?
Yeah, certainly. Well, it must be said that there are tools, and it is really important that the user understands the background. Otherwise, you're going to use a tool in a range where it's not applicable. And an important consideration is the particular tool, design tool, analysis tool, is it to be used in only potential flow or also in viscous flow? So I take an example, a very interesting and rather good program to design airfoils is X-foil. It has been years ago devised by Professor Drela from MIT. Works pretty well, very good way to design airfoils. You can run it in inviscid mode or in viscous mode. Well, inviscid, clearly you will not have the boundary effects, and therefore, especially if you look at drag, it's not good enough. But if you add the viscous calculations, the boundary calculations, then again you have to consider that maybe at low angles of attack is okay, at high angles, high lift, then the predictions are not accurate enough. So it's always really important to consider where the particular program can be used. 2D airfoil design is one thing, X-foil is one, Java foil is another one by Martin Hepperle from DLR. And you also have the need to run 3D analyses, wing shape. How do you do that? Well, there's various tools out there as well. Again, one from Mark Drela is a good one, AVL. It's openly available on the internet. But there also consider its limitations. It's mostly, say, potential flow analyses with some utilization of viscous effects. But it has its limitations. For low angles of attack, okay. For high angles of attack, close to CL max, you have to be really careful.
Okay. We already spoke about the lift to drag ratio, which is a measure for energy efficiency. How would you approach the design of an energy efficient aircraft? Because many of the design students have to be energy efficient, sustainability issues, of course.
Yeah.
How do you approach the design of an energy efficient aircraft?
Okay, so say that you had defined the mission and therefore the speed range and so forth. And by the way, low speed might be rather attractive because if you go for a very energy efficient aircraft, the lower speed is more attractive from energy perspective. Also because it allows the utilization of, for example, propellers. So people consider them old-fashioned, but propeller aircraft are really very fuel efficient. Say that you had decided that you want to go for somewhat lower speed and you utilize propeller propulsion, then suddenly also the aerodynamics of the propulsion system itself comes into play. So you have to be able to do an analysis there. You can say use a simple actuator disk approach or what's called the blade element method. It's really useful.
Yeah, this program Java Prop, is that the
Java Prop is a good example. You can use doing the first analysis of a propeller, of the performance and so forth, and certainly good enough for conceptual design. One other thing needs to be considered is how the propulsion system interacts with the remainder of the aircraft. In some novel designs, the propulsion system is closely interacting with the wing, for example. So if you would not consider what the propulsion system does on the wing, well, then maybe your picture is not complete. And nowadays, people are striving for what they call distributed propulsion, so multiple propulsors on a wing. And such a design certainly is influenced by the interaction between the two. So you would like to have some, as an example, you would like to take into account the increase in dynamic pressure coming from the propulsion system as it affects the wing performance.
Yeah, there's a significant effect on lift, I guess.
Yeah, there's a significant effect on lift because it increases the dynamic pressure. And you see some rather interesting designs appearing nowadays. Also, large companies like Airbus look into these kinds of designs. Furthermore, there also the propulsion system plays a role. Would you go for a hybrid electric design, for example? then suddenly you have to consider also the consequence on the weight, on the structure, the structural mass, to carry such a new propulsion system.
Okay.
Yeah.
Now let's take a step further. Let's look into unconventional designs. We see some on the posters
Yeah.
here on a
Yeah.
regular basis. New propulsion system. We already mentioned distributed propulsion. Unconventional platforms, flying V, blended wing body. How would you do that? How would you approach that at the conceptual design level?
At the conceptual design level, it sounds strange, but I would first, as a designer, start with simple hand drawings and show in a group and see what is the overarching, the overall design looking like. Here's a good example: a certain selection made by highly integrated systems. So the overall layout should be clear, and from there you dive deeper. You find that you have the need to design a good airfoil shape, but also a plane form, and then suddenly, as in this particular example, you see that the propulsion system plays a key role. You would like to know in how far there is interaction between your propulsion system and your wing. That's one thing for the performance. But secondly, how does it influence, and that's very important, the flight mechanical behavior of the vehicle? Because you could design something, it's from aerodynamic performance perspective, it's very good, but it cannot be handled or it cannot be flown in a stable manner, or you do not take into account, for example, system failure. What happens if this front propulsion system fails? And you have to take that into account.
Okay, so there's multiple aspects, flight dynamics involved, etc.
Yeah, indeed.
Okay, let's. I've already spoke about the tools that were available, methods, but now people always think about use of CFD, computational fluid dynamics. There's all kind of online solvers available. What is your opinion on that? Does it make sense or not?
Well, it's a good question because people do have the tendency to use the best and the most accurate software for their design. If you talk about computational fluid dynamics, there's all kinds of solvers out there, also commercial and non-commercial. They are very attractive if you're interested in the details of particular flow. But the consequence is it takes a lot of time to get a good result out there, so not very good, or maybe not even at all good for conceptual design. It takes a lot of time, and even in some cases they are not accurate enough. There's some simpler models, sometimes even handbook models, that are more accurate in predicting, for example, high lift behavior of a wing than a CFD solver would do. So I would certainly not recommend going into CFD solvers for such a design exercise.
Okay, so stay away from that.
Stay away from that. Use handbook methods. Use some of the tools, if you understand them, that can help you to design an airfoil, a wing shape, maybe even a fuselage or a nacelle. Simple methods, all available from, say, second and third year courses on aerodynamics. But stay away from CFD. It will just be too time consuming.
I saw that you also brought some other design books. Are these ones you would recommend for that?
Yeah, there's a couple of them that are interesting. We talked about the theory of wing sections. This is another one of Professor Torenbeek. This is actually a second book that he wrote, but the key one is synthesis of subsonic airplane design.
We have that available in our online library.
But also, if it comes to aerodynamics, a book like Aerodynamics for Engineers of Bertin contains a lot of useful information, even some sample programs which you may program yourself to do some quick analyses. And if you want to go a little bit deeper in understanding the tools, like how does a potential flow tool like X-Flow, for example, how does it work from the theory perspective, then a book like Low Speed Aerodynamics of Katz and Plotkin is a good reader. But it's it's not easy. It's not easy reading. So
it's a rather thick book as well.
It's a rather thick, but for reference purposes, it's good enough. But again, as I said before, I urge people to look into these tech books because they give the background where you can apply the method or not.
Okay, thanks. Last question for today. Are there any other important aspects you need to take into consideration when you talk about the aerodynamic design of your aircraft, your air vehicle? Any golden tips?
Well, golden tips is that first of all, I would say don't expect your conceptual analysis, aerodynamic analysis, to be very accurate. Take into account that it will be hopefully within a 10%, 15% accuracy range. That already from conceptual level is quite good.
And quite impressive, I would say.
Yeah. I would also say that to arrive at a design better than what's nowadays flying, and all groups strive to look at fantastic designs, know what you're talking about. So recap all of the key elements of aerodynamics. So what is a static pressure, dynamic pressure, how does it work, what is a induced drag, and so forth, and how would what a propulsion system or how does it operate. If you have the key understanding, then you can start working with them. If you would apply a tool just as it is and assume that the outcome is okay without checking and maybe using references, validating, that's quite dangerous.
So the message is don't overdo it, but really know what you're doing.
Don't overdo it. Check every step. Follow the recommendations given in textbooks and so. And certainly do not expect that in very peculiar situations like high lift, you have very accurate results. One last remark I would like to make. You can do very interesting things with aerodynamic shapes, especially if you look at low speed designs. You did some low speed designs. Then suddenly the boundary layer, the viscous effects, plays an important role. And you could nicely shape an airfoil such that it has a very good low drag performance. And for that you need special shapes. But there's a lot of reference material out there that can show you what plays the key role.
Okay, thank you very much for joining us today.
It was a pleasure, thank you.